All right. Now we are live on YouTube for lecture 20, part 2. So before we go over more questions on graphs, let's review a problem on combinatorics. Okay, so the first question is, what is the expected number of times a 6 appears when a pair of fair die is rolled 10 times? So this is a problem regarding expectations. Okay, and then this is a time where you should pause the video and see if you can solve this on your own. Okay, let's get to it. So to solve this problem, we're going to use a variable x, which corresponding to the number of successful trials. All right. For example, in this case, the number of successful trials is number 6 appears. It's a successful trial. Okay. Now remember, the equation for computing expectation is the expected thing for a random variable is n times p, where n is the number of times I'm going to roll the dice, which is equal to 10. And p is the probability I'm going to get a number 6. Because it is a fair die, so the probability of number 6 appear is 1/6. So this way I'm getting 5/3, which is the expected number of times you roll a die 10 times where a 6 will appear. So the main part of this question is actually using the formula, the expectation of a random variable. Okay. All right, let's move on to the next one. It's asking what is the probability that exactly 4 heads will appear when a fair coin is flipped 5 times, given that the first flip came up heads. So when you read this, one of the key point here is the word given, which means this is actually conditional probability. So again, please pause the video, see if you can solve this on your own, and then resume the video to look at the solution. So let's look at this again. If I'm thinking about conditional probability, I need to specify the events, the 2 events where one is dependent on the other. So there is 2 events. So first event, E1, is when first flip is head. So this is sort of this English statement translating to my variable E1, which is an event where the first flip is head. If I want to create a mental picture, this is the event where the first is head, and then there is 4 more flips. Now the second event is exactly 4 head appear in 5 flips. Okay, so this is exactly 4 heads appear when a fair coin is flipped 5 times. This is event 2. So event 2 is exactly 4 head appear in 5 flips. Okay. So what are some examples? For example, this is one example. Okay, but there's many instances. But then what the problem is asking for is conditional probability, which means what is the probability of E2 given E1? And this is the translation of the problem statement, right? What is the probability that exactly 4 head appear in 5 flips, given that the first flip is head? And now, as we recall, the formula for conditional probability is the number of times both E2 and E1 are true over the number of cases E1 happens. So now we just need to decide what's on top and what's on bottom. It's easier first to decide on what's on bottom, which is a probability that a first flip is head. So let's focus on the highlighted region here, right? If the first flip is head, it puts no constraint over the following 4 flips, which means for each of those location, right, you have 2 choices, either head or tail. So it's 2 times 2 times 2 times 2. That is the number of times that E1 might occur, which is 2 times 2 times 2 times 2. Okay, so what's on top? The top is both E1 and E2 happen. If both of them is happening, which means that, well, the first flip is a head and exactly 4 head appear. So if the first one is head, and I have remaining 4 location, but total I have 4 head, that means among the remaining 4 open slots, 3 of them will be head. Okay, so you choose among 4 possible positions, you're going to choose 3 of them and put head in there. For example, you can put the 3rd location head, the 4th location head, the last location head. That's one particular configuration. All right. Of course, the second one you can put into tail. So that is essentially C4 choose 3. Okay, that's exactly what we have. That's on top. 4 choose 3 is 4. The bottom is 16. So you get 1 over 4. So that is my conditional probability. Okay. All right. So now let's move on to questions regarding graphs. So this is sort of the detailed explanation of the solution as well. Let's move on to graphs. So what are some of the terminologies for graphs? If you have seen part 1 of lecture 20, you might have reviewed this again. So we're going to go through some of those terminologies quickly. First of thing is, what is a walk? Okay, a walk is just alternating vertices and edges, where the edge connecting its neighboring vertices. And it doesn't really have constraint, meaning that you can actually repeat the edge or repeat the vertices. That is a walk. Okay. So for example, if I want to be extreme, a potentially walk I can do is just go between Madrid and Paris and back and forth and back and forth. For example, if I go Madrid, Paris, back to Madrid, again to Paris, and back to Madrid, that is a walk. Okay. And that's walk. If I go back and forth 3 times, it has a length of 6, right? So the length of walk is the number of edges. And then finally, if it's closed, if that the first and the last vertex is the same. So a walk is a pretty general collection or list of alternating vertices and edges. However, the definition of the trail has a little bit more constraint. It is a walk with no repeated edges. And a circuit is a closed trail. Okay. Then a path, which is different from a trail, is a walk with no repeated vertices. Okay. So you might come to the same vertex, but you cannot you can use the same edge, but not the same vertex. So last one is a circle is a non-trivial closed trail in which the only repeated vertex is the first and last one. Okay, so let me take it back. If I pass is a walk with no repeated vertices, you have to be careful there, because in most cases you're going to have, if you allow repeat edge, most likely you will end up with repeated vertices. Let's see if we see any examples for the remaining of the talk. Okay. So first of all, let's look at this example. What is the number of vertices, number of edges? So this is a time where you can pause the video and try to solve this on your own. Okay. And now let's solve this together. How many vertices do I have? Okay. If I count the number of vertices, I get 10. What is the number of edges? It's a little bit tricky, so we need to count it carefully. So I'm just going to use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so that's 20 edges. Let me erase my markers. Is this a digraph? Meaning that does the edge has directions? The answer is no, because those are undirected edges. Specify the edge between vertex A and B. It's edge AB, which is highlighted right here in yellow. Is this graph simple? Remember, what is the definition of a simple graph? A simple graph is the one that does not have loops, right? What is a loop? It doesn't have something like this, or multiple edges. So what are multiple edges? This is a multiple edge scenario. So this graph is simple. Now give a walk from vertex E to vertex C, okay? I'm going to erase the yellow edge here. What is a walk from E to C? I could say it goes from E, H, J, and C. That's one potential walk, right? So if I write it out just by specify the vertices, it's going to go from E, H, J, C. Of course, I can do a more longer one. Okay, let's do a longer path from E to C. I can go from E to F to G to B and to C. Okay, and I can even go further. Maybe I don't end up with C. I go C, I, J, and back to C. That is also a walk because there's no much constraint over, it's allow repeated vertices and allow repeated edges. Now the next question is find a shortest length cycle. Okay, what is a shortest length cycle? If I'm looking at this, what are the paths that has the shortest length? My answer is 3. Going from A to G to B is and back to A is a shortest length cycle. The length is 3. So I go from A to G to B and back to A. And now the tricky question is, what is the longest? This is going to take a little bit effort to try to go over everybody. So I'm going to tell you right now, it's A, G, B, I, C, J, D, H, E, F, and A. So let's draw it in yellow. It's going from A to G to B, back to I, to C, to J, to D, back to H, E, F, and back to A. The longest length cycle is essentially the join of the star in this graph. Okay, what is the length? Assuming all edge is weight 1, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has a length of 10. Okay. All right. Let's move on to the next one. Now, I want you to find a walk from vertex 1 to vertex 8 that uses 5 edges, and it's not a trail, okay? So, recall the definition of a trail. It is a walk without repeated edges. So you're going to go through 5 edges, but you can't repeat them, right? But in this case, I'm saying it's not a trail. So that's actually where the tricky thing is. What is a example? So it's not a trail, okay? So that's actually not hard. Again, you should pause the video and think about this problem on your own, and then resume the video to look at the solution. So one example is I can go from 1 to 8, back to 1, and to 8, back to 1, and to 8. So pretty much I'm just going between 1 and 8 back and forth. So 1 to 8, back to 1, back to 8, back to 1, and back to 8. Okay, that is my walk. So this obviously is not a trail because I repeated the edge how many times? 5 times. Okay, so this is an example that is a walk from 1 to 8. They use 5 edges and it's not a trail. Okay, now let's ask a question for the particular graph we're given. Is this graph simple? The answer is yes, because it does not contain self-loop and it does not contain multiple edges. How can we specify a walk? Remember, when we just talk about walk, it's no constraint. You can just have an alternating list of vertices and edges. Okay, so now this is the first question here. Now the next question is, okay, if I want to do a trail, right? So now the second question, now if I want to find, there's maybe potentially another trail. Let's see if that is something useful. Let's say, can you find a trail that goes from 1 to 8? Okay, so the first question is find a walk that is not a trail. Now I want to find a walk that is a trail that goes from 1 to 8. Okay, it turns out this is also doable. You can go from 1 to 2, and 2 to 6, 6 to 5, 5 to 4, 4 to 8, and 8 to 1. Let's see, did I satisfy my condition? This is 1, 2, 3, 4, 5, and 6. Let me redo it. Oh, no, actually I don't come back. Correction, let me redo it again. The answer for this question here, if I want to find a trail, is go from 1 to 2 to 6 to 5 to 4 to 8. Oh yeah, I don't go back to 1. So how does it look like? 1 to 2, 2 to 6, 6 to 5, 5 to 4, and 4 to 8. That's it. That is a walk of length 5. So use 5 edges, and it is a trail. Okay. Now, finally, we want to ask a question is, can we find a circuit starting and ending at vertex 8 that is not a circle, okay? Not a cycle. So recall the definition. A circuit is a closed trail, and a trail cannot have repeated edges, okay? So now this takes a little bit effort to try to find this circuit, okay? So it has to start with 8 and will end with 8, okay? But as I mentioned before, a trail cannot have repeated edges, but you can actually repeat vertices. So that is a trick of this problem, okay? So let's give the solution here. The circuit that starts at 8, ends at 8, that is not a circle, is 8 goes to 4, goes to 6, goes to 2, goes to 3, goes to 4, goes to 5, goes to 6, goes to 7, and goes to 8. Okay, so let's use green to highlight this path, this circuit. Start from 8, it goes to 4, then it goes to 6, then it goes to 2, then it goes to 3, and 4, and 5 and 6 and 7 and 8. As I'm highlighting all the edges we go through in the circuit, you notice that we're not repeating any edges, but we can repeat some vertices, and it's closed. So that is your solution here. Okay. And also you can double check that this new circuit is not a circle, but is a closed trail. Okay, the next question is the question of what is an Eulerian graph, okay? And we'll come back to this page soon. But the whole concept came from the sort of the famous 7-bridge problem, right? So there is this city that has 7 bridges. It's connecting a piece of land in A, piece of land B, piece of land D, and piece of land C. So the question is it possible to take a walk using each of the 7 bridges exactly once? So the idea is to translate this problem into a graph problem where every piece of land turns into a node in the graph, and every single bridge turns into an edge. So for example, there is an edge between land C and A. So there is an edge between CA, but also there's 2 bridges between these 2 pieces of land, so there's 2 edges between them. So you basically translate this problem into a graph problem, okay? So the question is, can I have a walk that visit the edge exactly once? Okay. So let's now go back to the definition, the few definitions. Number 1, a trail or a circuit is a closed trail, is Eulerian if it uses every edge in the graph exactly once. Okay. Second definition, a graph is called Eulerian if it contains an Eulerian circuit. Okay. The last one, a graph G is Eulerian if and only if every vertex in G has an even degree. So this last thing is particularly important because it can be used to prove whether a graph is Eulerian or not by just looking at the degree distribution of its vertices. And we're going to see examples soon. So now, if I'm giving some examples, on the left-hand side, we're asking, what is the degree of the vertex A in G? Remember, the degree is number of adjacent edges. Again, you can pause the video and try to solve this on your own. The degree, in this case, it is adjacent to 4 edges, so the degree is equal to 4. Is H connected? The graph H is on the left-hand side. A graph is connected if there is a walk or a path from any node to another node. In this case, it's not because I cannot go from node G to node I, so the answer is no. Is H a subgraph of G? The answer is yes. Remember, when you say something is a subgraph, there is a mapping between vertices in H, two vertices in G, and from edges in H to edges in G. So let's check that. So we're claiming H is a subgraph of G. So A map to A, F map to F, G map to G. H map to H, J map to J, I map to I. That's not enough because that is just mapping between nodes. But we also have to have mapping between edges that is induced by the mapping between nodes. So correspondingly, we have edge AF map to AF. So there is an edge in H, and then there's a corresponding edge in G that map between A and F. Edge from AG map to edge in G. FG map into FG. HJ map to HJ, and JI map to JI. Okay. Now, finally, we're asking if my map G, my graph G, is Eulerian. Remember the definition on the previous slide. A graph is Eulerian if and only if every vertex in G has an even degree. So we just need to check if my graph has an even degree. So in this case, if you check, what is the degree for A? It's 4. Degree for B, C, D, E are all for 4. All the interior one all have degree 4. So all of them has even degree. So yes, this graph is Eulerian, because every vertex has even degree. Okay. All right. Let's move on to the next thing. Remember, there is 2 theorems we reviewed in part 1 of this lecture. The first theorem says for G being a connected graph, it's Eulerian if and only if every vertex in G has an even degree. Okay, so this is what we just used. The second one is a connected non-Eulerian graph has an Eulerian trail if and only if it has exactly 2 vertices of odd degree, and the trail begins and ends with those 2 vertices. Okay. So a trail, remember, is a walk without repeated edges. Okay, so we're going to use this soon. So now if I give you this graph, we're asking, is this Eulerian? Is there an Eulerian circuit? And is there an Eulerian trail? So again, please pause the video and try to solve this on your own. Okay. So first of all, is this Eulerian? If I want to check if a graph is Eulerian, I need to check the degree of all vertices. So the answer is no, because in this case, node A and H have odd degree. Because all vertices have to have even degree to be called an Eulerian graph. Now, you want to say if it contains Eulerian circuit. Remember, a circuit, the idea of a circuit is use every edge. Oh, the idea of Eulerian circuit, right, is to use every edge exactly once. Okay. And it turns out it does not contain an Eulerian circuit. So the answer is no. Okay. And finally, is there an Eulerian trail? Remember, we say it has a trail if and only if it has exactly 2 vertices at odd degree, and it begins and ends with those 2 vertices. So we know that the node A and node H both have odd degree, and they're the only one that has odd degree. And then we can try to have a trail that start with A and end with B. So the answer is, let me see if I can try to draw it. I go from A to B, and then B to G. G back to B, B to C, C to F, F back to C, C to D, D to E, back to D, and go through F, G, and H. Okay. Now, if I'm doing it slowly on the original graph, where is this Eulerian trail? A to B, B to G, G back to B, to C, to F, back to C, to D, to E, back to D, and then all the way to H. Okay. So the answer for this question is yes. And we kind of went through this proof before in part 1. The conclusion is if you give me any graph, the sum of the degree of all the vertices is twice the number of edges. Okay. Now the question, okay, now we have a practice problem, which is proofs involving graphs. There's actually many proof problems involving graph properties. So what is this thing asking? Giving a simple graph in which all n vertices has a degree of at least 2, there are at least n edges. So this practice problem is going to use the theorem 3, which is the sum of degree is equal to 2 times the number of edges. Okay. So please pause the video and see if you can solve this on your own. Okay. So to prove this, we can prove by contradiction. Okay. So how do we prove by contradiction? If we assume we want to prove the number of edges is at least n, but now let's assume the number of edges is smaller than n. Okay, and then this leads to some contradiction. Because the number of edges is smaller than n, and in the previous theorem, we know that the sum of all the degree of vertices is equal to 2 times the number of edges. Because number of edges is smaller than n, that means 2 times the number of edges is smaller than 2n. I'm just multiplying 2 on both sides of the inequality. So we know the sum of degree of all the vertices is smaller than 2n. That's what I get. However, because we say all the vertices has a degree of at least 2, by the definition, we know that degree of V1 plus degree of V2, because all those vertices, since each of them is bigger or equal to 2, right? Of Vi is all bigger or equal to 2. If I add them all together, that is bigger or equal to 2n. And this left-hand side is exactly the summation of all the degrees. So now this is a contradiction. Why? Because in inequality 1, I'm saying the sum of degree is less than 2n. And then in the second statement, I'm saying that the sum of degree is bigger or equal to 2n. Only one of them is true, right? Otherwise, there's a contradiction. So we prove that the original assumption is false. That means there's at least n number of edges. Okay. Now this problem is asking you to just draw the graph. It gives you the vertex set and edge set. Okay. Again, you can pause it and try to do this yourself, but this is pretty straightforward. I have A, B, C, D, E, F. And then there's edge between AB, AC, BD, BE, BF, CD, CE, and CF. Okay? That's how the graph looks like. However, I might make it prettier by drawing like this. But it's actually it's a slightly different drawing of the same graph. Okay. Now, given this graph, is this graph simple? You can pause the video now. Okay. The answer is yes, because it does not have self-loop. Also, it does not have multiple edges. Is this directed? The answer is no, because you don't have any directed edges. Everything's undirected. Now the question is, if I have a graph H that has vertices B, C, D, E, F, and edges that's given, is H our subgraph of G? What you can do is you can try to map all the vertices from H to the vertices in G, and all the edges in H to the vertices for the edges in G. Okay, so this is my graph G. And now let's map the vertices first. I have vertex B from H that is in G, C, D, E, F. Okay, so vertex map into each other. Now let's say if edges mapped into each other. Is BD mapped in here? Let's use green. Is BD in here? It's right here. BE, right here. BF. CD, CE. And the last one is a problematic one. It has edge FD, but graph G does not have this edge. So the answer is no, because H has FD that is not in G. Okay. Now let's ask more questions regarding walk. The length, is it closed? Is it a trail? Is it a path? Is it a circuit? Is Eulerian circuit if the graph is Eulerian? So all these problems can be solved by just looking at the definitions we showed earlier. Okay, so let's look at this initial path. Try to highlight in yellow. I'm going to go from B to E to C to A and back to B. So what is the length? Well, it goes through 4 edges, length 4. Is this closed? Yes, because it starts and end at B. Is this a trail? The answer is yes, because there's no repeated edges. Is this a path? The answer is no, because we repeat at node B. Is this a circuit? The answer is yes, because it is a closed and it is a trail. So a circuit is a closed trail. Is this a Eulerian circuit? The answer is no, because we did not use all the edges. And is graph Eulerian? The answer is yes, because every vertex has degree that's even, has even degree. Okay, so how does this Eulerian, remember when I say something is Eulerian, let's go back to the definition. Right, a graph is Eulerian if it contains our Eulerian circuit, and a circuit is Eulerian if it uses every edge exactly once. So now we need to figure out, can we go through this using every single edge exactly once? Okay. So let's use the color. I can start in B. I can go to B, to D, to C, to E, back to B, to F, to C, to A, and back to B. So in this is an Eulerian circuit that uses all the edge exactly once. Okay. And finally, let's end the lecture by looking at one more combinatorial problem. So in 1992, the announcer in a World Series said that the previous years, the team that won the first of the best 7 series won the entire series 60% of the time. The question is it surprising? We assume both teams are evenly matched, and suppose team A wins the first game. Then we need to consider what is the probability that A wins the series in 4, 5, 6, or 7 games. If it wins the first game, it also have to win the last game, okay? So to solve this problem, a good hint is to consider the possible configurations, which is this is a configuration where A wins after 4 games. This is A wins after 5, after 6, and after 7, okay? So the idea is to write out the combined probability. If you read the problem statement more carefully, right, this is actually a question regarding conditional probability again. It says the team that win the first of the best 7 series win the entire series. So it's essentially, if I want to derive it, okay, it's a conditional probability where event 1 is A wins the first game. Event 2 is A wins entire series after 4 games. And later we're going to ask what's probability, conditional probability after 5 games, after 6 games, and after 7 games. Let's do one at a time. The probability of E2 giving E1 is exactly the statement. Is the probability of A wins the entire series after a certain number of games, giving that A wins the first game. So of course, the formula is a number of instances for both events to happen over a number of instances where the first event happens. But we're going to do it for, after 4 game, 5 game, 6 games. Okay. So we're going to do this. Well, actually, let me compute it. The case number 1 is A wins after 4 games. It wins the first game, it also wins after 4 games. That means the configuration is just A wins every single game. So the probability is now equal to, using this formula, it only have one configuration on top. And because the starting point is A wins the first game, then there is essentially, right, if A wins 3 games, there is 3 more slots to fill the result of it, which is 2 times 2 times 2, which is 1/8, okay, which is 0.5 over the power of 3. Now the second case is A wins after 5 games. So first of all, let's look at all configurations. If A wins the first game, and I don't care about the rest, the bottom is 2 to the power 4th, right? And then the top is A have to win the first game, A have to win the last game, and then there's 3 positions in the middle. But total, A has to win 2 games. So in the middle, I can have 3 possible positions where I need to put 2 wins for A. So that is C of 3, 2. Okay, so C of 3, 2 over 2 to the power 4. Okay. The third one is A wins after 6 games. Again, let's look at all possible A wins first game conditions. So A, after it wins the first game, it has 5 location can fill, so it's 2 to the power 5. And A have to win the first game, the last game, in the middle. There's 4 positions. I can choose 2 of them for A to win. That is C of 4, choose 2. And of course, lastly, you can get if A wins after 7 games, what do you have? First of all, there is total of 6 empty positions to look at all configuration. That's 2 to the power 6. And it wins after 7 games. That means it wins the first game and the last game. And in between, there are 5 empty places. And among those 5 empty places, I need to allow A to win 2 of them. So that is C of 5, choose 2. Okay. Now, what we end up doing is we are adding each of those together, and that's roughly equal to 66% probability. Okay. So that's it. Have a good night, and remember, quiz number 4 is coming up next Tuesday on November 10th.